This is Module 9 on tensors, titled the Bilinear Map or generic Rank-3 tensor. I have written a text to accompany these lectures. A link will be placed in the description when it's available, hopefully soon. As always, I look forward to reading your questions and potentially corrections in the comments section below. Please share. So before we jump into the general Rank-3 tensor, there are a couple of mini topics that I'd like to discuss here at the beginning. One of those is tensor contraction as well as the tensor product. Now, unfortunately, we're not going to discuss these at length. The text, which will be available in the description below, provides some additional background on tensor contraction, as well as various tensor products, including the inner product, the dot product, outer product, Kronecker product, tensor product, and the traditional or contracted product. Now, in one of the previous videos, we did talk about the tensor product as well as the traditional matrix or contracted product. So if you need some background on those, you can go and check some of the older videos. But there are many other really good online resources that cover these topics, and that's one of the reasons why I didn't want to rehash that. I think there's a lot of great materials out there which discuss specifically these two, the tensor product and the contracted product, which we're going to be using in the upcoming modules. So if you need some background there, I encourage you to check out some additional resources. Now, this is very short. I just wanted to talk about some terminology. A map versus a form. So a map is an algebraic object that maps one primal vector space to another. It accepts a single input vector and generates an output vector. Actually, no. I should not write single here. I apologize, because it can be single for the linear map. Now, this is an object that maps one vector to another. We can also define a bilinear map, and that would map the tensor product of two vectors to a single, or essentially it maps two primal vector spaces to one. And then we can also define something called a multilinear map, which can accept more than two primal vector inputs. So we have a map as a general term, and then we can add a qualifier, whether it be linear map, bilinear map, or multilinear map. So this tells us what the output is, and these three terms tell us what the form of the input is. Now, in addition to the map, we also can define a form, and this is an object that maps a vector space to a scalar value, or a space that contains scalar values. We can use the similar qualifiers, so a linear form would be one that maps a primal vector space to a space that contains scalar values, and this is essentially a covector or a dual vector. That's what a dual vector does, right? Is it maps some primal vector to some scalar value. Now, what we're going to talk about briefly in this section is also something called a bilinear form, which you can kind of deduce what that name means, right? It accepts two input vectors and maps it to a single scalar output. And then we could also define something called a multilinear form, which then would accept more than two input primal vectors and map that to a scalar value. So just really some terminology here that we wanted to go over. Now, the bilinear form type tensor, initially I had planned on doing a separate video on this, similar to the linear map type tensor video. However, doesn't seem to be a huge amount of interest in that, so I decided to sort of provide a very brief overview of what a bilinear form is, and then recap some of the topics touched on here in this section, which I'm going to talk about the real topic of this section in a minute. But really quickly, what is a bilinear form? Right, we've already seen it defined here. It's essentially an object that generates a scalar output, accepts two primal vector inputs, right? We multiply that by our G represents the bilinear form type tensor, and again, right, we generate our scalar output. Now, it's important to note here that we must employ proper contracted ranks. If you're not familiar with what that means, you may need to take a look back at some supplementary materials on tensor contraction as well as the contracted product. But in short, perhaps this relationship is best shown by the summation form. Now, so up here we have a tensor general form, and down here we have a summation form. As these tensors get more complex, higher rank, you'll see that the summation form often tends to be a better description of what's going on. Now, why is that? Because if we look here, we can see specifically how the elements of the tensor are multiplied by the elements of the input vectors, and specifically we can see how the indices match up, right? So we see that there's a correlation between the contravariant index of VA and the first covariant index of G, and a relationship between the only contravariant index of VB and the second covariant rank of G. And that's what we're saying up here in the green and purple statements, right? G times VA indicates that we're multiplying we're contracting with respect to the first contracted covariant rank of G. And for the second product, or G times VB, it's contracted with respect to the second contracted covariant rank of G. All right, you can see that down here, right? First contracted covariant rank of G, second contracted covariant rank of G. So if you're ever having a little bit of trouble understanding an expression like the one above, one recommendation that I have is to try to look for a summation-based form, because they can often provide a, I don't want to say more accurate, but perhaps a more descriptive representation of the input-output relationship. Now, for the rest of these slides, I'm going to go through them very quickly, if talking about them at all. Here we can see the general form and structure of this tensor, of the bilinear form, and the way that it's constructed. Whereas the linear map, right, was rank 2, having one contravariant and one covariant rank, the bilinear form essentially has two covariant ranks. So what we end up with is a row-oriented array that contains row-oriented arrays as sub-elements. So I don't want to get too caught up here, or else this is going to turn into a video on the bilinear form. If I read stuff in the comments saying that there's a lot of interest in discussing the bilinear form, I will come back to it at some point. We could also expand that discussion into talking about the metric tensor, which is another very useful tool in in the realms of physics and multiple other areas. All right, so I think we have a basic understanding of the bilinear form, very basic. You also see again here I have a MATLAB example, so if you are able to get access to the textbook when it's available, you would also get access to the MATLAB example of the bilinear form. So let's jump into this generalized rank 3 tensor and what that means, how we're going to use that, and talk about why we're even discussing this. Up to this point, we've presented tensors in terms of specific types, like a primal vector, a dual covector, a linear map, a bilinear form, although we only talked about this one very briefly. Beyond the vector, the primal vector, and the dual covector, these classifications are largely unnecessary and don't have a really concrete meaning. We know that a vector is a representation of a value in some n-dimensional space, and the covector is the most fundamental mapping between that vector and another value, which in that case would be a scalar. But the linear map, the bilinear form, multilinear map, multilinear form, these descriptors don't have the same concrete meaning, and what we're going to try to do is stop using those terms, at least temporarily, and describe a tensor in terms of its covariant and contravariant rank. So instead of saying linear map, we're going to say contravariant rank 1, covariant rank 1, algebraic object, or tensor. For bilinear form, we could call it covariant rank 2 tensor. Now we're going to have some drawings in a second that's going to explain what that means, so don't get put off by the language. And then equivalently, we can describe any tensor as the product of fundamental vectors and covectors, and this relates directly to the contravariant and the covariant ranks. So in short, all of our tensors are really just different combinations of vectors and covectors, and that's the reason why I call these two the most fundamental. So in this section, we're going to describe the characteristics of our rank 3 tensor, which we could call a bilinear map, right? It could be a bilinear map because it is taking, it is accepting two vector inputs and generating a single vector. So this makes it a map, and this makes it bilinear. But in general terms, we want to talk about how to increase or decrease the various ranks. So looking ahead to the next video, that's what we're going to focus on. So let's introduce this rank 3 example. We want to understand how higher rank tensors may be defined in a generalized manner. Now, I have seen some textbooks that try to write one equation that describes any generalized tensor. I think obviously that's accurate, but it can be a little bit difficult to understand, and so we're going to take a slightly different path when it comes to that generalization. What we're going to do, just looking ahead for 1 second, is we are going to define a certain tensor, and then, well, specifically a rank 3 tensor, okay? And we are going to demonstrate what happens when we increase the contravariant rank by 1, or we decrease the covariant rank by 1, or vice versa, decrease contravariant, increase covariant, and sort of use almost like a recursive algorithm here where we show for any given tensor structure, covariant, contravariant ranks, how can we increase or decrease either of those ranks, and what effect does that have on its mapping, on its structure, and its use. So you could hypothetically use that to build any tensor, right? If you start off with a rank 3 tensor, you could build a rank 49 tensor by following these rules. So perhaps won't be as concise as what other texts present, but I think it will be a little bit more understandable conceptually. So what we're going to do is we're going to expand the bilinear form to rank 3 through the addition of a new contravariant rank. Now, one shortcoming of this video is that it does base a lot of things off the bilinear form with the assumption that we were going to spend a lot of time discussing the bilinear form, which we really didn't. However, it's okay. What I can do is translate these explanations into terms of a linear map, and I'm going to do that as we move forward. So this rank 3 tensor is equivalent to taking our bilinear form and adding a new contravariant rank. So let's take a look at what that means. So let's start off by talking about a bilinear form. So a bilinear form, right, is a covariant rank 2 object. And so what we have is something like this. All right, and I mean, obviously the size is just generic, so it doesn't really matter here. We have a row-oriented array with sub-elements that are row-oriented arrays. So the outer layer would represent the first covariant rank, and the embedded layer, like the sub-elements, would represent the second covariant rank. Now, when we say we're expanding or increasing the contravariant rank, that's equivalent to giving this more rows. So now, right, what we end up with is a rectangular matrix that is composed of these little row-oriented arrays. So this is what the structure of our rank 3 tensor will look like. Now, we can do a similar expansion from the linear map, right? Because we started off with a linear map that was simply just something like this. And again, size is irrelevant. It doesn't have to be a square. Okay, and this has contravariant rank 1, covariant rank 1. If we wanted to add a second covariant rank, which is how we would go from the linear map to our rank 3 tensor, what we would do then is expand the individual elements sideways, okay, because we're adding a covariant rank. So every place I had an X, I now make that a row-oriented array of multiple X's, or multiple scalar values. And I hope that I don't need to even finish this. You should be able to see that these two match. So what does this show? This shows that whether we add a contravariant rank to the bilinear form, or whether we add a covariant rank to the linear map, right, both of those changes lead to a similar type of rank 3 tensor, okay, which has, not to be repetitive, a contravariant rank of 1 and a covariant rank of 2. We require one index to tell which row we're on and two indices to tell which column, because we need to know which outer column we're in as well as which inner column we're in. So this also provides a preview of what the structure of our rank 3 tensor will be. Okay, so this is a little bit of recap, right? Adding a contravariant rank to the bilinear form is equivalent to replacing the scalar y out with a vector that we call v out. Okay, so one side effect of making this expansion is, whereas previously we just had a single value being generated, that would become an array, a primal vector, a column-oriented array containing different values. So the result is the input-output relationship that we're going to show on the new slide, the next slide, for a new rank 3 tensor, which we call T. All right, so this is the general form. We have an output tensor, primal vector v out. We have two input vectors, which we call VA and VB. We can imagine them as taking the tensor product of those and then multiplying that by T. And then this tensor is our general rank 3 tensor. And we've already talked about how this tensor can resemble both the bilinear form and the linear map. Now the summation form, as I said previously when we discussed the bilinear form, right? This summation form is, I think, a lot easier and a lot more accurate of representation of this relationship up here, where again, we can see how the contracted product is being implemented, where the elements of VA are indexed with this index k. They correspond to similarly k index values within the tensor T, and then we have M and M. Or, in short, right, we are taking the product of VA with respect to the first contracted covariant rank of T, and VB with respect to the second contracted covariant rank of T. Now this, up here, this is the new index that we see when we compare it back to the bilinear form, and this will tell us what vertical element we are looking at in our output vector. So this is really just our first look at this tensor. Let's take a chance to dive into more of the details in the structure. So I think this is similar to what we've shown already. Up here we have a bilinear form, and we showed that by adding a contravariant rank, right, or increasing that contravariant rank to 1, we're adding more rows to the tensor. Similar to how when we had our linear map, right, we added to generate this rank 3 tensor, we had to add a covariant rank, and that stretched everything out sideways. Okay, so now we want to define this generalized rank 3 tensor in a similar way to that applied to the linear map as well as the bilinear form. And we need to define some fundamental values or some assumed values here in order to do that. So let's first talk about the basis. What are the basis, or what is the basis set for this rank 3 tensor? We expect the basis set to contain algebraic objects whose structure match that of the tensor, meaning it should have contravariant rank 1 and covariant rank 2. But that's not the most fundamental definition. Like how we did for the linear map, we need to define basis sets for our output vector as well as both input vectors. So V out, the primal vector, is composed of its pre-transform basis set as well as its pre-transform coordinates. The input A, product of its pre-transform basis set as well as pre-transform coordinates, and the same thing for VB. If you remember, this subscript right here is simply telling us what the associated bases are. And then down here, all we've done is simply take these values and substitute them into the equation here. Since we're going to spend more time diving into this type of expression, I'm going to put off a more detailed explanation for a minute or two. So we know that the basis of this rank 3 tensor is somehow going to be generated from or based on 3 different primal basis sets, right? That associated with input A, that associated with input B, as well as that associated with the output. Now, as we've seen previously, some of these will have to be inverted. Specifically, and if we look back to the linear map, we have to invert the basis, or we have to understand what the inverted value is for the basis associated with the inputs. Not going to explain why at this moment. We will see again in a second, but if you go back and look at the linear map lecture, you can get an additional explanation there. So what we're going to do is define B pre-A inverted as well as B pre-B inverted. And since we can visualize the inverted primal basis set as dual basis sets, I can go ahead and call it beta pre-B, beta pre-A, as well as beta pre-B, right? The primal basis set is a row-oriented array with column-oriented elements, and the dual basis set is a column-oriented array with row-oriented individual sub-elements. All right, so these are the basis that we're going to use to generate the basis set for our generalized rank 3 tensor. Essentially, we have the non-inverted primal basis set associated with the output, as well as the inverted, right? This is the same as B pre-A -1. This is the same as B pre-B -1. As well as the inverted basis sets associated with both of the inputs. And again, we're just showing the general structure here. And then here is how we generate the basis set associated with our linear map with our rank 3 tensor. Essentially, it's the tensor product of the B pre-A inverted, B pre-B inverted, and B pre-out not inverted. So first input, second input, and output. And what we do is we take every permutation of those products. So essentially this would be 1, 1, 1. Then we would move on to 1, 1, 2. Then 1, 1, 3. Until we reach the maximum for that index. Then this would return to 1. And then we would increment that to 2. And anyway, hopefully you can see how this would progress until we end up with the final basis algebraic object, which would have the last basis vector, or really covector, associated with the first input, last associated with the second input, and last associated with the output. So NA represents the number of bases associated with input VA, and B the number of basis, individual basis vectors associated with VB, and NC, which I guess I really should have called N out, but the number of basis associated with the output. And here's just an expanded version of that, where we can see, again, if we look at our understanding or recall our understanding of the tensor product, the first element is simply this times this times this, right? And then the second element would be this times whatever the second one may be. Then this times the third element, and you end up, once you go all the way to the end, the last one times the last one times the last one. So the number of bases would be equal to NA times NB times NC. That's the number of algebraic objects you would expect to be inside of this structure right here. So below we have, we demonstrate how to perform the required tensor product. This may be useful to those of you that don't have access to a text that talks about tensor product in depth. But anyway, this is generalized. So we're taking the tensor product of the kth dual vector associated with the first input, the mth dual vector associated with the second input, and the pth primal vector associated with the output. And I know the terminology can be a little bit tough here. I'm almost getting tongue-tied saying it myself. Anyway, and you can see here how the individual elements are then multiplied. And the colors hopefully help to demonstrate where matching values are employed. If we assume that all bases are orthonormal, okay, then the Kronecker delta function, which I'll talk about very briefly in a second, assigns a 0 value to all elements for which indices do not match. So what's the Kronecker delta function? It's essentially a function where it generates two values, a 1 and a 0, a 1 if k is equal to m, and a 0 otherwise. So that's what the Kronecker delta function is. And so what we're saying is, taking the equation up above, if all the bases, and that's b pre a, b pre b, and b, that's b, what do I call it, pre out. If all of those are orthonormal, and if the primal bases are orthonormal, then their associated betas will also be orthonormal, so you don't have to worry about both. If these are orthonormal, then what we're going to end up with is that these products will only contain 1s and 0s, and we will end up with a basis set that looks like this. Okay, very similar to what we saw for the linear map. So we have a set of structures, each one with contravariant rank 1, covariant rank 2, but that only contain a single value of 1. Right? Because in each one of these algebraic structures, there'll only be one of these products where all three of these values are a 1. Okay, right? If any one of these three values is a 0, then it will knock the whole product down to 0. So I apologize for not going into the calculation of the individual elements here. If it's something you want to see, please throw a comment in the section below, and I'll try to come up with something. All right, so now that we understand what the basis set is associated with this tensor, we can discuss how we can define that tensor in terms of a coordinate matrix as well as a basis set. And this is a recurring theme that we're going to see throughout this whole discussion of tensors. And probably one of the things that I most want to convey to the audience is that the tensor is always composed of some combination of a coordinate array or coordinate matrix or some sort of coordinate algebraic object, as well as a set of basis vectors, covectors, or basis algebraic objects. And that's what we have here. So this is our coordinate matrix or coordinate algebraic object, and here is our basis set. So now this is in a summation form, which we like. And so let's talk about the different parts. So the tensor, the resultant tensor is over here on the left-hand side. We are using the bidirectional arrow hat to indicate that this is neither a primal nor a dual vector. It's a higher rank tensor, and so it's composed of both primal and dual vectors. Okay, so in the green, we have the coordinate matrix of T, or specifically element PKM of that. And that is defined with respect to the basis set below. And so that's why it's included in this subscript, with this subscript note. Okay, so we take that and we multiply that by the kth basis of covector beta pre-A, okay, the mth basis of beta pre-B, so kth basis vector, mth basis vector, and then the pth basis vector of B pre-out. And so we expect that to generate an algebraic object with the size equal to that of the coordinate matrix, as well as equal to the size of each element of the basis set. Essentially, the size of the covariant rank will be n out, although I guess previously we called this nc, but so nc, let's just assume nc is equal to n out. The first covariant rank has a size or a length of na, and the second covariant rank has a size or a length of nb. So again, we see a very similar structure where we have a tensor that's composed of the product of some coordinate algebraic object and basis, and that's what we apply to the primal vector, to the dual vector, linear map, bilinear form, etc. So now we want to talk about this generalized rank-3 tensor as a vector-covector product. We may define the coordinate matrix T. So remember that T with the arrow hat, that's the tensor, and the T without the arrow hat, that's the coordinate matrix or the coordinate algebraic object. We can define it as the tensor product of two row-oriented coordinate arrays, all right, and one column-oriented coordinate array. So this changed from the bilinear form to the map, and it also changed from the linear map to this rank-3 object. Whereas before, for the linear map, that could be defined as the tensor product. So linear map could be defined as the tensor product of some generic primal vector times some generic covector or dual vector. The bilinear form was the tensor product of two different types of covectors. And then for this rank-3 tensor that we're looking at, this will be a single covector times two covectors. And so I'm going to call these the more fundamental vectors and dual vectors. So this makes sense because row-oriented covector coordinate arrays would be associated with the dual-like basis sets B pre-A and B pre-B. So it makes sense. We have two of those input basis sets, and as such, we have two row-oriented covector coordinate arrays. We have two subscript indices. And we have only a single column-oriented vector coordinate array as an input, and that's associated with the single contravariant index that we have as a superscript. So the equation on the next slide demonstrates that matrix T, again, no arrow hat, okay, is defined in terms of these bases, which we've already went over, and it may be decomposed into the tensor product of three more fundamental arrays. And that's essentially what we show right here. Right, the linear map can be decomposed into, and here I use tensors, so perhaps I should call them arrays, but you get the idea. Essentially, we have a column and a row-oriented array, two row-oriented, and then we have column and two row-oriented. And so this is what we're talking about when we discuss that fundamental decomposition. And so here is a better representation of that. So the number of vectors and covectors, okay, should correspond to the number of contravariant and covariant ranks respectively. So if you are looking or trying to classify a given tensor, right, and we know that it has two covariant ranks and one contravariant rank, that also tells us that the coordinate matrix can be generated from two row-oriented arrays and one column-oriented array. Or we can generate the overall tensor as the tensor product of a single primal vector and two covectors. Right? There's a very strong relationship between 1, 1, 1, 2, 1, 2. And that's also reflected in the indices of the coordinate matrix, where we have 1 up top, 1 and 1, and then we have 2 covariant indices, 1, 2, 1, 2. So we may define tensor T in terms of these vectors and covectors. And so all we've done here is replace what's in this slot. Instead of referring to it as a coordinate matrix, we can refer to it as this product of 3 more fundamental arrays, 1 being a column-oriented and 2 being row-oriented. So now going back to change of basis, because we know that one of the most important characteristics of a tensor that we need to understand is how does it react to change of basis, both the basis themselves as well as its coordinate matrix. So to maintain our tensor input-output mapping, meaning that we always want V out to be equal to the tensor times, okay, that should never change regardless of how any of these individual bases change. Okay, if we want this tensor expression to be maintained, we have to apply an appropriate transform to the coordinate arrays as well as the coordinate matrix. So the equation below, this tells us how to transform one single element of our coordinate matrix, which now we can call T post. So T pre would be the, I would assume, looking at my naming, this would be the coordinate matrix before the transform, and then T post, that would be the coordinate matrix post transform. And I was almost going to put an arrow here, but there should not be an arrow there. Okay, no arrow, no arrow. Remember, only the coordinate matrix, the coordinate matrices can transform. The tensor itself is invariant to change of basis. All right, so what do we have? Okay, the post-transform coordinate matrix, which we call T post, is equal to the pre-transform coordinate matrix, which we call T sub pre. And we multiply it by 3 different transformation matrices. We have the forward transform matrix associated with the input, the forward transform matrix associated, well, with the first input and the second input, and then we have the inverted or the reverse transform matrix associated with the output. Now we've already defined these matrices. If you go back all the way to here, actually I think we may not have defined it yet. Well, I can do that really quick. Right, we have this right here, B pre A. I think the reason why I didn't define it is because we've kind of already set an assumed notation. But if we wanted to define one of those as an example, we would see that B post A, okay, after the transform, would be equal to the transform matrix, and we always use a superscript to indicate the ID of the pre-transform, and we use a subscript to indicate the ID of the post-transform, and then B pre A over here. So these are the matrices that we're referring to on that next slide. And you know, we could change the A to a B, and then we could replace the B without. And essentially, right, we have 3 different transform matrices. And that's an important thing to realize about these higher rank tensors, is that we're not defining a transform, in my opinion, or at least the way I would word it, we're not defining the transform associated with that tensor. We're really defining the transforms associated with the inputs and the outputs. Okay, the desired input and output types as well as their desired spaces, and then we're combining those together to create the transform for the tensor. Okay, so let's go back over here where we were, and what we will see is, if I can get back to my spot, is right here you can see our transform matrices. So we define the transform matrix for the first input, transform matrix for the second input, as well as the transform matrix for the output. So B post pre out is equal to F pre post out inverted. Okay. And so now the one thing I haven't talked about is that this is a summation form right here. So we're actually not transforming the whole matrix in one step. We're actually dealing with individual elements. So to talk about that for 1 second, what this equation actually does is it calculates element P, K, M, a single element of the post-transform coordinate matrix in terms of, now you can see here that these subscripts don't match these subscripts because this is defined in terms of the post-transform basis, this in terms of the pre-transform basis. Okay, so this is a single element of the post-transform matrix. This is a single element of the pre-transform matrix. And what we're doing is multiplying by a single element of the reverse or the backwards transform matrix associated with the output, as well as a single element of the forward transform matrices associated with the two inputs. And if we follow this equation, what it does is it updates all the elements of our coordinate matrix. So if we only manipulate the basis of a single input, like let's say we're only manipulating the basis of the first input, then this will be an identity matrix and this will be an identity matrix, and you only need to consider that element. All right. So we've talked about the transform. We know already how to define the reaction, or how does our rank-3 tensor coordinate matrix react to a change in the basis of either one of the inputs as well as the output. Now we want to define the tensor in terms of the transform matrices. And all we really have to do for that is essentially just add the basis. So all this equation is really saying is that we can define our tensor in terms of the post-transform coordinate matrix and the post-transform basis. Or, as we did before, we can define it, I don't know how far I'm going to have to go back, in terms of the pre-transform coordinate matrix and the pre-transform basis. So you see the form of this equation right here, defined in terms of pre-transform values, is exactly the same as the form of this over here. Sorry, one more. Of this right here, which is then defined in terms of post-transform. The most important thing to note here is that these bases must match these bases in order to generate a consistent tensor output. Again, this is in summation form. So next, let's try to define the tensor in terms of the transform matrices. So far, what we've done is we've defined the coordinate matrix in terms of the transform matrices. We've defined the tensor in terms of, and I wouldn't really say this is in terms of the transform matrices, this is more so in terms of the transformed values. And then next, all we're really doing is just substituting in our individual transforms. So the equation below demonstrates that tensor T, right, may be generated in terms of the pre-transform coordinate matrix and the pre-transform basis, or the post-transform basis and transform matrices. I think we've shown that already sufficiently. Now, the tensor product space, we talked about this briefly when we discussed the linear map. And what we saw was that the tensor product space is analogous to the primal vector space or the dual vector space, right? It represents all potential functions that accept a certain number of input vectors and generate a certain number of output vectors, or in this case, a single output vector, right? The primal vector space was the combination of all potential vectors, primal vectors. The dual vector space was the combination or the collection of all potential dual vectors, mappings of that primal vector space to a scalar. And so this tensor product space, which is really a generalized description, okay, it's a generalized way of saying this is the space associated with our rank-3 tensor. It contains all potential functions that act on a pair of input vectors to generate a single output vector, as described here, or all potential mappings between the rank-2 primal space and the rank-1 primal space. Okay, with this being the input and this being the output. And so below, we define the most fundamental scaling and addition rules associated with that space. Okay, here we define our mapping. Here we define an addition rule, which essentially says that we can distribute the addition, and instead of applying our function, what is f of t? Right, that's just essentially a functional description of our rank-3 tensor. So when we say f of t VA VB, that's the same as taking our tensor and multiplying it by VA tensor product VB. It just is an easier way of writing it. Okay, so we can distribute this addition and then apply our mapping 2 times with V1 and V3 or V2 and V3. So we can either sum the inputs internally or we can sum their individual outputs. We can do the same thing for the other input, right? So this is for the first input, this is for the second input, and then we also have a relevant scaling rule, which says that if we scale the output of the function, that's the same as scaling either the first or the second of the 2 inputs. So why examine another tensor? Okay, why are we taking a look at this bilinear map? We've already discussed the linear map. We've already discussed the bilinear form vector. And the reason is, and we've talked about this previously, is this is going to serve as the base case for the next section, in which we are going to add and remove ranks, both contravariant and covariant, to and from this bilinear map, okay, this rank-3 tensor. So the idea is we have some familiarity with this rank-3 tensor. What we're going to do then is increase the rank to go to rank-4, take a look at how that affects the structure, then downgrade it to rank-2 and see how that affects the how that affects the structure and its behavior. So in this way, we hope to demonstrate how tensors may be generalized. Instead of creating some really long equation with all kinds of, generic number of indices and, all kinds of complex notation, which I'm probably not well versed enough in mathematics or formal mathematical definitions to do that. Instead of doing that, we're going to take this recursive approach, where we're going to define a base case and then look at how things change when we increase or decrease the number of covariant or contravariant ranks. So for example, this would be analogous to wanting to build a high-rise. Okay, instead of providing some generic description of a high-rise, what I can say is, here's a 3-story building. I'll tell you how to add a floor. I'll tell you how to subtract a floor. And if you understand both of those, they apply uniformly to any size, you can build any height of building that you want. If you have a 49-story building, you know how to add an additional floor. If you have 51, you know how to remove a floor. And so that's the same methodology that we're applying to the contravariant and covariant ranks. So this module really serves as a precursor, as a setup for the next module. Here, in this one, we talked about this bilinear map, this general rank 3 tensor. We talked about its behavior, about its structure, about its input-output mapping. And the next module, I think we're going to get to a more interesting topic, which is how do we extrapolate that? How do we expand that to cover other contravariant and covariant ranks? So, I mean, we just presented that building example about building a 50-story building by adding floors to shorter buildings, and I think that analogy works here. So it should be very interesting for us to look at different characteristics. For example, input-output relationship, and show 5 different cases. Okay, what is the base case that we had for our rank 3 bilinear map tensor? What did that input-output relationship look like? Then we change it, we manipulate it, adapt it so we have one higher contravariant rank. So it goes to contravariant rank 2, covariant rank 2. Then we do the opposite. Subtract one contravariant rank, which essentially brings it back to a bilinear form. Anyway, then we do the same thing for covariant rank, increasing and decreasing it. So we're going to take a look at the mapping. We're going to take a look at its structure. We're going to take a look at its basis. We're going to look at all these different characteristics of a tensor and present 5 different cases for each. What's the base case? What did it look like for the bilinear map for the general rank 3 tensor? What does it look like when we increase contravariant rank, decrease contravariant rank, increase covariant rank, decrease covariant rank? So I've looked over these notes several times, and I think it provides a pretty robust explanation of how the size, the complexity of a tensor can be generalized in this manner, and I think you should find it really enlightening.